We're now going to move on from considering first order ODE to higher order ODEs, primarily second order equations, but occasionally we're going to venture to equations of even higher order. And the most comprehensive theory for these higher order equations can be developed for linear equations, and that's what we're going to discuss now. So first, let me remind you what a linear equation is. It's anything that looks like an of x times the nth derivative of the function y plus n minus 1 of x times n minus first derivative of the unknown function y plus etc. plus a2 of x y double prime plus a1 of x y prime plus a0 of x times y, and all of that is equal to another function of x, which we will label as f of x. So this is, as you might recall, an nth order linear ODE. All right, so if I find the general solution of, if I can find the general solution of this linear equation, then I would expect something that contains n unknown constants. And then in order to determine these constants, we will have to prescribe, for example, initial conditions. So let's discuss a corresponding initial value problem. So the corresponding IVP initial value problem is, so it's going to, as usual, consist of the equation itself. So we can copy it into this new location, plus initial conditions. And so we need, in this case, because it's an nth order equation, we need n initial conditions. So we start by prescribing y at some initial point x0. So that's obviously not enough, that's just one condition. Then we continue, y prime of x0 is equal to y1, you keep going. So in this case we start from 0 of derivative, then first derivative. So at the end of the day I need n conditions. So as we discussed before, that means that I'll have to stop at n minus first derivative. So y n minus 1 of x0 is going to be y n minus 1, and then overall we prescribed n conditions. And so then presumably this IVP will have a solution, and we ideally want a unique solution. So I would then like to know in advance whether or not a unique solution of this initial value problem exists or not, just like we did for the first order equation, because if you can just take a look at your IVP and see that it does have a unique solution, then you then can go ahead and try to solve the initial value problem either numerically or analytically. So can we guarantee that the initial value problem like this has a solution or not? And apparently we can, and we can formulate the following result. So note let's say if the initial point x0 belongs to some interval, let's say AB, and AI of x, where I can be any number from 0 all the way up to n, are all, in fact, even more, and AI of x, and f of x. So all of these things are all continuous functions of x on this interval AB, and too many n's, but whatever, and an of x is not equal to 0 on AB, then this IVP has a unique solution. All right, so if our initial point belongs to some interval and all coefficient functions are going to be continuous on this interval, and the leading coefficient function an of x does not vanish on this interval, then we can guarantee that the initial value problem will have a unique solution, so then it makes sense to try to solve it. So, for example, let's do a couple of examples. So, for example, if I take the equation, let's say y double prime plus 3y prime plus 2y equal 0, and maybe y of 0 is equal to 1. Now, this is a second order equation, y double prime. This is a second order equation, so in this case I need two conditions. The last condition is going to be y prime of 0. Let's make this equal 0. So if I look at the initial value problem like this, can I guarantee that this has a unique solution? So the coefficient functions, so in this case, the coefficients functions are a2 of x is equal to 1 everywhere, a1 of x is equal to 3, and a0 of x is equal to 2. And in fact, f of x is equal 0. They're all constants, and therefore they're all continuous. In fact, not just continuous, but continuous on all real line, right? Continuous for all x. Likewise, a2 of x, in this case a leading coefficient, is never equal to 0 because it is equal to 1. And so then, by the previous observation, a unique solution of this IVP exists. Okay, so since I know this, let's say that, suppose that now someone told us that y of x equal to c1 e to the minus x plus c2 e to the minus 2x is a solution of this ODE. We have done that before, right? That's easy to do. You just need to take first and second derivative. So if y is like I have just written, then y prime of x is going to be minus c1 e to the minus x plus minus 2 c2 e to the minus 2x by the chain rule. Y double prime of x is going to be c1 e to the minus x plus 4 c2 e to the minus 2x, again by the chain rule. And then if I substitute this into the equation, so substitute into the ODE. So y double prime is c1 e to the minus x plus 4 c2 e to the minus 2x plus 3y prime, so plus 3 times minus c1 e to the minus x minus 2 c2 e to the minus 2x, right? That's y prime from here. And then plus 2y to c1 e to the minus x plus c2 e to the minus 2x. That is my y. So now if I distribute everything, here I'm going to get c1 e to the negative x plus 4c2 e to the minus 2x minus 3c1 e to the minus x minus 6 c2 e to the minus 2x, and then plus 2 c1 e to the minus x plus 2 c2 e to the minus 2x. And then I can combine the similar terms. For e to the minus x, we have c1, so this is gone, minus 3c1, this is gone, plus 2c1, so that is gone. And for e to the minus 2x, we get something similar. 4c2, gone, minus 6c2, this is gone, plus 2c2, that is gone. And then, of course, 1 minus 3 plus 2 is 0, so this is 0. 4 minus 6 plus 2 is 0, so this parenthesis is 0. So whole thing is 0, so that means that my function, indeed, my function y of x equal to c1 e to the minus x plus c2 e to the minus 2x, indeed satisfies this equation. Well, so then I can try to use the initial conditions to solve the initial value problem right here. Oops. So this is the initial value problem I'm trying to solve. So what is y of 0? Y of 0. So then y of 0 on one hand, I want that to be equal to 1. And on the other hand, it is this expression with x being equal to 0. So c1 e to the minus 0 plus c2 e to the minus 2 times 0. And then I know that y prime of 0 I want to be 0, right? That's my second initial condition. And y prime of 0 is given by this formula. So minus c1 e to the minus 0 minus 2c2 e to the minus 2 times 0. So we have these two equations, and we can simplify them by observing that all exponentials here are raised to the power 0, so they all must be 1s. So c1 plus c2 is 1, and then minus c1 minus 2c2 should be 0. And now we just solve for c1 and c2, so one thing that we can do is add the two equations. So if I add them, I'm going to get, I'm going to get 0 minus c2 equal to 1, so therefore c2 is minus 1. And then from the first equation I have that c1 is 1 minus c2, so 1 minus minus 1, so 2. And so then the conclusion is that the solution to the IVP, to my initial value problem, is again given by this expression here, which I'm going to copy. And I have to replace c1 and c2 by these numbers that I found. So c1 is 2, and c2 is minus 1. So this is what we're going to get. And now, because we discovered that the solution to this initial value problem is unique, and so then we can conclude that this is the only solution. There are no other solutions. All right, so this is what we have. Maybe let's try to do another example. And another example is going to be this. Let's look at the equation like this. Y double prime plus pi square y equal to 0. So this is a second order equation. It is a second order linear. Actually, one more thing that we learned before, that for second order linear equations, if the right hand side is 0, we call this equation homogeneous. If the right hand side is not equal to 0, then we call the equation non-homogeneous. Again, I'm going to emphasize that this is not homogeneous in the same sense as those equations of the first order that we solved by using substitution. So from now on, in fact, homogeneous would always refer to linear equations with 0 right hand side. So this is a second order linear homogeneous equation. And so if, and actually one more thing, the coefficients in this case are 1 and pi squared. 1 and pi squared are constants. So those are continuous functions on all of R, and so that means that if I prescribe any initial conditions, so let's say if I try to solve the IVP, initial value problem, consisting of this equation, y double prime plus pi square y equal to 0, y of x0 is y0, y of x1 equal to y1. If I try to solve the initial value problem like this will always has a unique solution. From our observation above. Right, again, 1 and pi square are continuous functions, 0 is a continuous function, and 1 is not equal to 0 because the leading coefficient should not be 0. All right, but then an alternative to IVP, you may or may not recall that we have already discussed this, is going to be this. I can try to prescribe my two conditions not as a function and a derivative at a single point, but as I can prescribe the value of a function at two different points. So for instance, I can say that y double prime plus pi square y equal to 0, and then y of x0 is still equal to y0, but I can also prescribe y at some other point, x1, and say that this is y1. So what I'm doing in this case is, let's illustrate this graphically. When I'm prescribing an initial value problem, what I'm doing, I'm prescribing an initial point, x0, y0, and at this initial point, I'm prescribing also the slope, y prime of x, right? Actually, I did make a boo-boo here. Y prime of x0 is equal to y1. I'm sorry. So that's the initial value problem, because otherwise I'm still writing a boundary value problem. So I'm prescribing the initial point, and I'm also prescribing the initial slope. That is equal to y1. And then the claim is that if I have an ODE and I prescribe the initial point and the initial slope, I can always reconstruct the solution. So here I'm doing something different. So that's IVP. And for BVP, we're going to do something different. Still, I have a set of axes, x and y. But now, what I'm doing, I pick 2 points, x0 and x1. At one of them, the value is going to be y0. At another one, the value is going to be, of the function, is going to be y1. And what I'm trying to do is I'm trying to find a solution curve that connects these 2 points. So this is a boundary value problem. And so let's see on particular examples what sort of things that we can expect when we solve boundary value problems. So first of all, I'm going to consider some boundary value problems. Examples. So first, I'm going to notice something here. So first, I'm going to observe that y equal to c1 cosine pi x plus c2 sine of pi x is a general solution of my ODE. Not of the initial value problem, but of the ODE of y double prime plus pi square y equal to 0. So we check that in the usual way, right? We need to figure out the second derivative and then substitute the function and the second derivative into the equation. Let's check that. So y prime is minus pi c1 sine of pi x, the chain rule, plus pi c2 cosine of pi x, another application of a chain rule. Then the second derivative, y double prime. Again, I take a derivative of sine of pi x, I get cosine of pi x, and chain rule says pi comes out, so we get minus pi square c1 cosine pi x. And then the derivative of cosine of pi x is minus pi sine pi x, so minus pi square c2 sine pi x. And then I can factor out pi square. So this is, in fact, I can factor out minus pi square. So minus pi square c1 cosine pi x plus c2 sine pi x. And then who is c1 cosine pi x plus c2 sine pi x? That's nothing but my y. So this can be written as minus pi squared times y. But if y double prime is equal to minus pi squared times y, bringing pi squared y to the left side, you will get y double prime plus pi squared y equal to 0, and that's your ODE. So indeed, what we have is, so this checks out. All right, so we have the solution of the ODE, and I'm going to use that solution to solve a couple of boundary value problems. So consider a boundary value problem like this. Y double prime plus pi square y equal to 0. And then maybe y of 0 is equal to 1, and y of 1 is equal to 2. How would I solve the boundary value problem like that? So let's call this BVP 1. Well, I already know that the solution is y equal to c1 cosine pi x plus c2 sine pi x. So then, if I evaluate y at 0, I want that to be 1. And I want, at the same time, y of 0 to be c1 cosine pi times 0 plus c2 sine pi times 0. Okay, so that's the first condition. And then the second condition, y of 1, I want to be equal to 2. So that will be c1 cosine pi times 1 plus c2 sine pi times 1. Okay, so we now have two equations for two unknowns, which we're going to simplify. So first of all, what is cosine of 0? Cosine of 0 is equal to 1, right? And sine of 0 is equal to 0. So what we get is that C1 times 1, this must be equal to 1, right? So once again, C1 times 1 plus C2 times 0 equal to 1, so C1 is equal to 1. That's the first equation. What about the second equation? Second equation says cosine of pi is minus 1. Sine of pi, again, is 0. So the second equation becomes minus C1 is equal to 2. Or that means that C1 must be minus 2. Well, but isn't this a problem? Because now what we have is that from a second equation, C1 is equal to minus 2. From a first equation, C1 is equal to 1. And that is a problem, right? Because C1 cannot be equal to two things at the same time. So that means that what we have is an impossibility. And from that, we conclude then that my boundary value problem number 1 does not have a solution. So this immediately contrasts boundary value problems with initial value problems. So basically what we were saying before is with the initial value problem, I start at a given point, I send curves from that point at different angles and reconstruct the solution completely. I found my solution. What's the difference with boundary value problems? Well, if I start sending solutions from this point at different angles, in principle, I am not guaranteed that any of those solutions will end up going through this point, right? So maybe they're all going to go somewhere to plus infinity, or either plus infinity or minus infinity, but they're never going to pass through this second point. So that is a difference between initial value problems and boundary value problems. That it is possible that boundary value problem does not have a solution, even though you're solving the same very nice equation, y double prime plus pi squared equal to y, plus pi squared y equal to 0. For initial value problems, always a solution. For boundary value problems, possible that you don't have a solution. Let's consider another example. Same equation, y double prime plus pi square y equal to 0. And now let's suppose that I have y of 0 is 0 and y of 1 is also 0. Okay, so how do I try to solve this boundary value problem? In the same way, I know that the general solution looks like this. And so I can substitute my boundary conditions into this equation. So first of all, y of 0 is equal to 0. What do we have? Y of 0 on one hand is 0. On the other hand, it is C1 cosine pi times 0 plus C2 sine pi times 0. Y of 1, which also is 0, is equal to C1 cosine of pi times 1 plus C2 sine pi times 1. All right, so what are we going to get from those? Still, just like before, sine of 0 is 0. Cosine of 0 is 1. So from the first equation, I have C1 is 0. What about the second equation? Sine of pi is still 0, cosine of pi is still minus 1, so from a second equation I get minus c1 equal to 0. Well, but so both of these equations tell me actually the same thing, that c1 is 0, right? Because I can divide the second equation by minus 1 and I still get c1 equal to 0. So c1 is equal to 0, and nothing can be said about c2 because it's always multiplied by sine of pi, or by sine which is equal to 0. So c1 is 0, and then c2 is arbitrary. And so then we conclude that a solution to this BVP2 is what? It's my expression here with c1 equal to 0 and c2 equal to anything. So it is y equal to c2 sine of pi x. And because c2 is undetermined, any c2 will do. So what I have is infinitely many solutions. And so therefore BVP2 has infinitely many solutions. Any multiple of cosine of sine of pi x is a solution of this boundary value problem. So that again is not really very nice, because if you're using your boundary value problem to predict a behavior of some physical system, then you probably wouldn't really like the fact that your physical system then can have infinitely many different types of behavior. All right, and a third example going to be BVP3. So let's take again exactly the same equation. Y double prime plus pi square y equal to 0. Y of, let's say, y of y of 1 is equal to 0, and maybe y of 3/2 is equal to 0. Okay, let's try to solve this third boundary value problem. It's going to be BVP3. And again, I have to follow exactly the same strategy. So y of 1 on one hand is 0. On the other hand, it is referring back to the same formula for y of x. On another hand, it is c1 cosine pi times 0 plus c2 sine pi times 0. And then y of 3/2 also is supposed to be 0, but on the other hand it is c1 cosine pi times 3/2 plus c2 sine pi times 3/2. What does this mean? It means that, so again, cosine of 0 is 1, sine of 0 is 0, so c1 is supposed to be 0. And then from the second equation, I'm going to get that 0 is equal to cosine of 3 pi over 2 is going to be 0. So C1 times 0 plus sine of 3 pi over 2 is minus 1, so minus C2. Regardless of what C1 is, C1 times 0 is 0. And so what we get is that both C1 and C2 should be 0. And if both C1 and C2 are 0, then from this we can conclude that y of x should be 0 times cosine of pi x plus 0 times sine of pi x. So overall that is 0. So y then identically is equal to 0. And that's the only solution of BVP free. So the conclusion from this discussion is this: a boundary value problem may have one solution, right? Like in the last example. It may have infinitely many solutions, like in the second example. Or no solutions at all. So in that sense, solving a boundary value problem is more challenging than solving the initial value problem. For initial value problem, for a nice equation, we always guarantee that you have a solution. But even for a nice equation, the boundary value problem may or may not have a solution, or it may have one solution or infinitely many solutions. And in fact, boundary value problems actually are as important as initial value problems. For instance, if you want to determine the motion of the bridge, right? So if you somehow think about your unknown function as a height of a given point of the bridge above the river, then if the shape of the bridge can be described by a function y of x, then, and you can construct some ODE for that function, then clearly where the bridge meets both sides of the river, right, then there the bridge is fixed. So on the shores, y of x is going to be fixed, and between the shores, its shape is going to be variable. So that means that in order to find the shape of the bridge, you will have to solve a boundary value problem. So then in the next lecture, we're going to continue discussing the theory of linear equations of a higher order.